everyone, I hope you are doing good. So today we will take a new DSA question here, and the question is print leaf nodes from pre-order traversal of BST. So one binary search tree pre-order traversal data would be given to us, and then we have to basically print all the leaf nodes. We have to find all the leaf nodes from that pre-order traversal of the BST, right? So let's take one example here to understand the question. So here the question is pre-order data is given. This is the input, right? 5, 2 and 10. And here if we basically the diagram of the BST is this one, 5, 2 and 10. So 2 and 10, these are the leaf nodes. So these two nodes should be there in our result output, right? So that is what it is getting here, 2 and 10, right? Let's take another example. So here this is another example where the pre-order data is 4, 2, 1, 3, 6, 5. Right, this is the pre-order data, and this is the diagram of the binary search tree, right? The basic condition of the binary search tree is the left node value must be less than the root node, and the right node value must be greater than to the root node, right? That is what, and it applies for each and every node. That is what the base condition of the binary search tree. Correct? I hope you know this one. So this is the diagram of the binary search trees, and then 1, 3 and 5, these are the leaf nodes, right? Leaf node means that node should not have the either left or right. If it is having either left or right, then that is not a leaf node. So for example here this 2, it is having left also, right also. So 2 cannot be a leaf node. And this 6 is having left, right, not right, but it is having left, right, it is having one child node. So then 6 cannot be a leaf node, right? So that is the basic definition of the leaf node. That leaf node is the last node that cannot, or that is not having the either left or right. The 1, 3 and 5, these three are the leaf nodes, right? And those are coming as a output. So from us also the expectation is from our algorithm is that it should identify all the leaf nodes, and then it should basically add those leaf nodes into one vector, and then we can return that vector as an output. That is what is expected from our algorithm. Correct? I hope it is clear to you. Let's take one more example here. So this one. So here this is the diagram of the binary search tree. This is the pre-order, right? I hope you know how can we basically get the pre-order data, right? I have explained this pre-order, post-order, in-order, level order, right? These traversal techniques I have already discussed in multiple videos, but so you can go through those videos and watch that, right? So here let me quickly show you how we get it. So we draw the line left side, right, for pre-order, and right side for post-order, and below for in-order, right? So how we are getting pre-order is this one, and we start tracing from top of the tree from here, right? So let me change the color. So here, so for example here, so 8 is getting crossed first, right? So here we will print 8. Then go down here, 2 is getting crossed, so we will print 2. Then go down, 5 is getting crossed, then we will print 5. Then nothing there down, so then go left, right, nothing is there, then go up, right, go back to down here, and here 10 is getting crossed, so we will print 10. Then we will go down here, 12 getting crossed, so we will print 12. And then nothing is there down, nothing is there right side, right, go up, nothing right, go up and back to the top of the tree, right? So we have traversed complete tree here, right? So and here our output is 8, 2, 5, 10 and 12, right? That is what is giving pre-order data, right? So if you have any query or doubt like how we are getting this pre-order, so this is how we get the pre-order, right? So I hope it is clear to you. Now think about the solutions. How can we solve this problem? And if you get any solution other than different than whatever I will discuss, then please comment below the video so that we can also get benefited by your solution, whatever you think. So here let's take this example and try to write an algorithm here for this one. So what can I do here? What I will do basically, I will take one stack, and initially I will push this stack the first element of the pre-order, because we know that the first element will always be a root of the binary search tree if we see the pre-order traversal data, and in post order the last element would be a top of the tree or root of the tree. That is what we know, right, already. So I will push the tree. I will call it P only. So P of 0, right, and then I will take one vector here, right, vector res we can say, right. Here in res I will store the data result, right. Now what we can say, after this I will start the loop to traverse complete pre-order data from the first index, because the 0th index we have already taken and we have already pushed it into the stack, right. So let's take this one. So this 8 we have already pushed here, correct. Now I will take a loop here. So let's take for loop. I is from 1 to n, right, and here what I will do, I will check if uh, pre of I, right, that is the current element p of I, right. I is starting from 1 to n. So this is the current. If current element is greater than, if the current element is basically greater than the top of the stack, then we will go inside this if block, right. And what we will do in this if block, we will basically take the last pushed element into the stack. So that is the top of the stack. So that is st dot top, right. And then we will add a while loop here, and we will check if stack is not empty, right. And the second condition is this one, the p of I should be greater than, right, if current element is greater than the top element, correct. So if this is the case, then we will basically pop out the stack element, stack st dot pop, right. So here in this case 8, now this current is 2, right. 2 is not greater than this one, so we will not go inside this one, right. So that is why, and after this what we will do, this is we will complete the and also what we will do here in this if this while loop, we will basically maintain a PC count, popped element count, and we will do plus plus, and PC will start from 0, right. How many elements we have popped out, correct. And then what we will do after this, if PC is greater than 1, then we will add the last element whatever we have basically taken out, or last element we have pushed into the stack, to the we will add that to the result array, right. So result dot push back and this last, that is what we will do. And then we will close this if here, right. And after this if this is not the condition, if the current element is not the greater than the top of the stack element, in that case we will directly insert that into the stack. So in that case we will say stack dot push and then p of I, and then we can close the for loop. And after this, if stack is not empty, if stack is not empty, right, then just add that element, the top of the stack, to the result array. Then just add res dot basically, or you can say push back, and then stack dot top. So here I am just adding the algorithm here. I am not following the syntax and all those things. I am just try to understand the logic behind the solution basically here, right. And then we will close the for loop here. So here what I'm doing, first I'm taking one vector, right, res, and one stack st, right. And in stack what I will do initially, I will basically insert the 0th element or the first element of the pre-order traversal data. Why? Because the first element of the pre-order traversal data would be the root of the binary search tree, right, that we know, right, already. So now I have initialized basically with the first element of the pre-order traversal data to the stack. then I will start traversing this complete remaining pre-order traversal data from the first index to the nth index, right? So for that I am taking one loop here, 1 to n, and here what I will do, I have added one condition, if condition, where I will check if the inserted elements, right? Let's dry run parallelly. So I have added 8 here already. Now I am here and I will start the loop, right? And I will take and I will check this. This is the current element now. P of I, P of 1, that is 2. 2 is greater than the top of the stack. No, it is not. So what I will do, I will skip this complete if block, this one, and I will directly insert this into the stack. So I will add this to here, correct? Then what, then I will go next here, right? Because this is a for loop, right? So I will go next here. 5 is greater than the top of the stack, yes, right? Because top of the stack is 2 and the current element is 5. P of 2 is 5, right? So 5 is greater than this one, so this condition is fulfilling. So we will go inside this block, if block, and we take the last element, right? So here what we can say here, our last element is 2, right? And then we go inside this while loop and we will check stack is empty. No, stack is not empty. And the current element P of I is greater than top element, yes, it is, yes, it is greater than 5 is greater than 2. So we will go inside this while loop and we will pop out the first element. So what we will do, we will pop this out and we will increase the PC count plus plus, right? So PC now becomes 1, right? PC is popped element count, correct, 1. And this while ends here only, right? So now from here to here, so these two statements are there in while only, popped element, right, and the PC count plus plus. And now again we will check the condition, stack is empty. No, stack is not empty, but the P of I is 5 and the top of the stack is 8, right? Top of the stack is 8, so 5 is not greater than 8. So this condition is breaks here. So we will go down and here check PC count is greater than 1. No, it is not greater than 1. So we will skip this statement also here, right? Why I am adding this PC count is greater than 1 is that, for example, here we have only popped out one element. So what does it mean by one element here is that we have popped out only 2 and then the condition is false, right? And then what we are doing here, we are pushing the element, current element, right, to the stack here. So here what we will do, we will insert this 5, right? So we can say that this 5 is greater than 2. It means this should go to the right of that, basically it should go the right side, right? Now we have to decide for which node it should go to the right side, right? So here we have popped out one element 2, right, but it is less than the 8. So it means it should go to the left of the 8 and right to the 2, right? Because what is the basic condition of the binary search tree? If the node, if the value is greater, it means it should go to the right side. If it is less, then it should go to the left side. Now the 2, right, the node with value 2 is less than 5, so the 5 value node should go to the right side, but it is less than 8. It means it should come from the left of the 8, right, and right of the 2, right? And so here this is the only remaining place, and here it is showing it is right of the 2 only, correct? So that is what we can decide from by seeing the data here. I hope it is clear now. If right, and if it should have, we should have popped more than 2 elements, in that case what we can say, that this should becomes the leaf node. 5 we have already taken, right? So now our current becomes 10. Here we have popped out 2, so let me remove this one also, 2, and let me add 5 here. So now this is our current element now. So now 10 is greater than 5, yes, right? So we will go inside this one, this if block, right? The top of the stack is 5 and current is P of I is 10, right? So last element, let's take this in last. So instead of 2 here, now take 5, right? That is what the last popped inserted element 5, and reset this PC count also to 0, right? And then we will check the while condition here. ST empty, stack is empty. No, stack is not empty, it is true, condition is true, right? and then p of I is greater than top, yes, so we will pop this element, right, and just increase pc by 1, right, and then again go and check if the stack is empty. No, stack is not empty, and the p of I is greater than top, right, p of I is greater than top, yes, 10 is greater than 8 also, so we just pop this out and increase the pc by 1 also, so it becomes 2, correct, and now stack is empty, so we are coming out from this while loop condition. So we are coming out from this while loop, and here we are checking pc count here, right. So now this time this see pc count is 2, so what we will do, we will add this element, last element is 5, so we will add this 5 into the result array, right. In result array what we add, this 5. Why we are saying? Because here we know that we have popped more than one element, it means the last element whatever we have pushed into the stack, that is the leaf node, and that is what it is, right. 5 is the leaf node, right, because we have popped out 5, so now the current is 10, right. So 10 is greater than 5, greater than 2, right, it means sorry, greater than 5 and greater than 8, right, and it is greater than 8, it means it should go to the right of the 8, right, it should go to the right of the 8, right. Then what we can say, 5 is the leaf node, because the left side we do not have left node of the 5, right node also we do not have, because we have popped 5, right, and we have popped 8 also, and 8 must be greater than 5, right, that is why it is there. So in that case we can say this 10 is not the right of the 5, and either it is not the left of the 5, so 5 is the leaf node, that is what we can consider basically, right, conclude. And to identify the leaf node, we are adding here this condition, this pc count, pc must be greater than 1, then that node is the last node whatever we have pushed, that is the leaf node, right. I hope it is clear to you. Now increment and then we insert the last element, right, the current element, that is 10. So we have popped 5 and 8, right, and we have inserted 10 here, correct, and we are here in, now here 12 is greater than the last element, yes, we will go inside the C block again and we will take the last element. So here the last element is 10, right, that is the top of the stack, and let me reset this pc count also. So here pc count is 0, right, and then we will check stack empty, no, stack is not empty, true, current element is greater than, yes, it is true. Now st.pop, let's pop this out 10, right, and pc count becomes 1, and then again we will go and check stack is empty, so we will come out from here and pc count is 1 only, right, so we cannot say that 10 is the leaf node, right, and then from here we will come out and we will insert this element here 12, right, 12. Now we are done with complete preorder traversal, right, so we will come out from this for loop and we will check if stack is not empty. Stack is not empty, it means some data is there, right, and whatever the data which inserted last, right, into the stack, that would be the top of the stack, and the top of the stack data is the rightmost tree, that is what we can conclude, because this is the last data. And when we check for preorder also, so you can see here, if we go this way, right, so this is the node which got encountered last, it means this is the last node, or you can say rightmost leaf node, right, that is what we can conclude, this is the rightmost leaf node, correct. So that is why we have added this one condition here, right, here this condition, if stack is not empty, then consider the top of the stack as a leaf node and just add it into the result, right. So we will add this 12 into the result and this would be your result. I hope you are clear with this algorithm. Let me show you the C++ code also, there also I will explain it. So here you can see the C++ code, and here we are getting this preorder data, right, I am taking size here, taking one vector, one stack, and initially I am pushing the initial like the first element of the preorder traversal data to the stack, and that is what I have already explained, because this is the root of the binary search tree, so that is why we are pushing directly it into the stack, right, and then we are taking one loop here from one index to the nth index, right, that is what I have already explained. Then I am taking current node to the current node variable here, and I am checking here the condition. This is the if condition, right? I have already explained. So here I am checking if current node is greater than the stack node. It means that the current node should go to the right side, and now left node, whatever the smaller nodes that can could be popped out from the stack, right? And here we will identify for the leaf node. So here smaller nodes count I am taking here, right? I have explained for PC count, popped element count, right? The popped elements are smaller, so that is why I am calling it small nodes here. And then leaf node, I will say I will take this as a top of the stack here in leaf node, right? And then I will check here in while loop, stack is not empty and the current node is greater than the top of the stack. It means that we have to pop the element from the stack, right? So here smaller nodes, I will increment this integer variable smaller nodes plus plus, and I will pop the element from the stack here, and I will do it until either the stack is empty or the current node is smaller than the top of the stack, right? It means this condition breaks. Until then I will doing the pop-up, and once we are done with this one, then I am checking here for the leaf node. If smaller nodes are greater than 1, right? If the smaller node counts are greater than 1, it means that the last inserted element, right, that is the leaf node, right? And that leaf node I am inserting into the result array here. That is what I already explained into the algorithm, right? And then after this what we are doing here, we are just adding the current node into the stack here, correct? Now this is our for loop, right? And after once we are done with this for loop, then what we are doing, then we are checking for the last or you can say rightmost leaf node. If stack is empty, then we can ignore this one. If stack is not empty, right, if stack is not empty, then we are just basically adding that push back the st top, the top of the stack, we are adding into the result array, right? And then we are returning this res here, resultant vector, correct? I hope it is clear to you, and this is the same implementation of that algorithm into the C++ code. If you have any query, doubt, please comment below the video. I will address your comment query there itself, or I will take those queries in the upcoming video, right? Yeah, thank you for watching the complete video. See you next time. Till then, keep learning and keep exploring.